As platform engineers and SREs, managing a unified observability pipeline means dealing with multi-tenancy. You have multiple teams, microservices, and environments sending logs, metrics, and traces to a centralized OpenTelemetry Collector cluster. The challenge is not just ingestion, it is routing. You need to inspect incoming payloads, whether by HTTP headers, gRPC metadata, or resource attributes like service.namespace or tenant.id, and dynamically direct them to distinct backends. For instance, production traces must go to a highly available Jaeger or Tempo cluster, while staging data goes to a cost-effective cold storage bucket. Doing this at scale, with minimal CPU overhead and zero data loss, requires a deep understanding of the routing mechanisms available within the OpenTelemetry Collector. To understand routing, we must first review the internal architecture of the OpenTelemetry Collector. Traditionally, the collector operates on a simple directed acyclic graph: receivers, processors, and exporters. Receivers ingest data, translate it into the internal P-data representation, and pass it synchronously to processors. Processors perform operations like batching, filtering, or attribute manipulation sequentially. Finally, exporters translate the P-data back into the target format and send it over the wire. Crucially, pipelines are strongly typed. A trace pipeline only processes traces, a metric pipeline only metrics, and a log pipeline only logs. They run in isolation. If you wanted to generate metrics from traces or route data based on complex logic, this rigid structure presented a significant architectural hurdle. To solve the routing challenge, the community introduced the routing processor, found in the OpenTelemetry Collector-contrib distribution. The routing processor acts as a pseudo-exporter within a pipeline. It intercepts the telemetry stream and evaluates routing rules based on context, such as incoming HTTP headers or gRPC metadata, or resource attributes using the OpenTelemetry Transformation Language, or OTTL. For example, you can define a rule where if the X-tenant header equals tenant alpha, the data is routed to the OLTP/tenant alpha exporter. If it matches tenant beta, it goes to OLTP/tenant beta. This allowed platform teams to achieve multi-tenancy within a single pipeline configuration. While functional, the routing processor introduces several architectural and operational drawbacks. First, because it behaves like an exporter, it must be placed at the very end of a processor chain. This means any routing decision bypasses subsequent processors in the main pipeline, forcing you to duplicate processing logic across multiple downstream pipelines or handle it entirely upstream. Second, it tightly couples routing logic with exporter definitions. If a downstream exporter experiences back pressure, the routing processor's internal queue can fill up, potentially blocking the entire pipeline and affecting other tenants. Finally, configuring complex routing rules in a single processor block quickly leads to massive, unmaintainable YAML files that are prone to syntax errors and difficult to unit test. Now, we integrate this connector into our service pipelines. In the service section, we define our primary pipeline, traces. Its receiver is OTLP, its processor is memory_limiter, and its exporter is our connector, routing/tenant router. Next, we define our tenant-specific pipelines, traces/tenant A and traces/tenant B. Crucially, the receiver for traces/tenant A is the connector itself, routing/tenant router. This pipeline then has its own processors, like batch/tenant A, and its own dedicated exporter, like OTLP/tenant A. This structure completely decouples the ingestion and routing phase from the processing and exporting phase of each individual tenant.